If you didn't see my last video, it was about inertia, and it was explaining how the ocean of matter was responsible for inertia of both rest and motion. Gravity's the same way. The gravity is also caused by this ocean of matter that we're all in. It's like we're all fish in an ocean of matter that we tend to not even believe exists because we move through it so easily, but it's very dense. We're just like a screen door, and most of it just kind of passes right through us, but we can push on it, and it can push on us, as I demonstrated, as you may have experienced with inertia of rest and motion. Now, gravity is very similar to inertia, rest, and motion. You can even simulate gravity by using inertia. Like, for example, on a space station, you could have swirling around, like you could have an astronaut here, and he could be swirling around inside like a dome, and he could be going around like, the dome could be going around like this, and he could be inside, and he could be experiencing, inertia of motion, keeping him stuck to the side as it spins around, and he could feel, and it could feel like gravity to him. But that's not gravity. Gravity is not a flow of matter. It has to do with the same particles as inertia, and that's why inertia and gravity feel similarly. But gravity is more like a field. There's no such thing as fields, and there's no such thing as fundamental forces of nature, and there's no such thing as properties to matter. There's really only one property to matter, and that's just that matter just is. It exists. And so when you look at matter, it's just stuff, and the ocean of matter that we're all in is just stuff. It's just the stuff, like the same stuff that physically speaking, we're made of. So when you're looking at gravity, gravity is also caused by this ocean of matter that we're all in. Now, gravity is an interesting thing. You jump up, and it sucks you right back down, right back to the earth. You jump up, and you go down. Why do you go down? Well, the reason why you can go up, is because you jumped up. You established a flow in the matter, and as soon as your feet left the ground, that flow of matter that you established helped keep you going up in the air once your feet left the ground. But then gravity overcame that flow of matter and brought you back down. It overcame inertia of motion. Why? Why does gravity pull you down? Why does gravity cause all larger objects to come together in the universe? For example, the Earth seems like it's attracted to the sun at a distance, but nothing attracts at a distance, not even gravity. No, there's no such thing as a force that acts at a distance, but only things that are pushed in by what's right, connecting them, what's right pushing in on them, and that's where this ocean of matter comes into play. To understand the basic principle as to why gravity brings matter together, you would have to understand why any large objects come together. To understand this, it's best to demonstrate with some spheres or balls. I'm going to call them balls because everyone knows what a ball is. Let's see. So, here you have a soccer ball, and here's a large piece of matter. Now, the best way to cover a large piece, actually let me demonstrate with a smaller ball. Okay, here's a ball, and to cover this ball the very best, what you do is you cover it with something that's concave, that looks sort of like a cave, like if I cup my hand like that. see how it's like cupping the ball. So if you had something that like you put the ball in a cup or something like that, that would be the very, you know, best way you could cover the surface of this ball, is to like coat it all the way around like that. There, that's the best way to cover the ball. But what if you didn't have a cup or a cave or whatever you want to call it? What if the only thing you had was a flat surface? Then a flat surface would be the best way to cover the surface of the ball. The most efficient arrangement would be a flat surface. As you can see, it doesn't cover very much of the ball, though. It only covers just where the flat surface, you know, goes, and it goes around. And you know, that's a, you know, that's still a more efficient arrangement than if you didn't have a flat surface. Or if you didn't have a flat surface, what if the only thing that you had to cover this ball was the opposite of a cave? What if all you had was another large ball? Now you can see it's almost like a flat surface to this ball because this ball is so big. So this ball, to help cover this ball's surface, in order to avoid holes, the best thing you can do is a large ball. And in the universe, there aren't flat spaces and there aren't concaves or cups for balls. The only thing that you've got is other larger balls. So, between the cracks of the balls, you know, that make up the ocean of matter that we're all in, as, you know, say, you know, see here some balls, when they come together like this, you know, right between them, you can see that crack right there. And in that crack right there, between the balls, there's a little, you know, the crack is pretty small because, you know, like you can probably see the three balls here. See there? See how the green ball is poking up into the crack? Now, that's poking up well into the crack because it's such a small ball. This ball here, it doesn't poke up into the crack very well. See how much larger that crack is compared to the green ball that poked up into that crack. So, this arrangement isn't very efficient for the small balls to be on the larger ball all by itself. What fills this hole better is to have larger balls. So you can see that the smaller ball didn't cover this ball's surface very well. But if you had other larger balls, you could cover the surface of this ball much better, especially if you had a lot of balls, of course. There. But even this, you know, even though it helps cover the ball's surface better, larger balls help cover the ball's surface better, it's best, of course, to have a combination of different balls to cover the surface better, or the best. There you can see that a combination of the balls, both the big balls combined with the small ball, you know, is still a large ball. And then if you can imagine more balls on top, would make a very efficient arrangement of balls, covering the surface of the other balls in order to cause no cracks to be there. And you have to remember that the ocean of matter that we're all in has pressure to it. And it's constantly pushing in and pushing out all the cracks. That is all the empty space. So that's why gravity happens, is because it's the most efficient arrangement of balls. And that's simply it, is that the larger balls will cover each other's surfaces better. See, that covers the surface of the soccer ball. You know, this volleyball covers the surface of this soccer ball, see, a lot better, combined with other balls, of course, than does these smaller balls, which cause, as you can see, a much larger crack. Yeah, you can probably see that larger crack there. And it's because this ball doesn't poke up into that crack, that hole there. And so, this is more efficient. You can see that the hole becomes much smaller because this is poking up into the hole. So larger balls demand larger balls to be around them. In other words, larger pieces of matter demand larger pieces of matter to be around them. And the reason for that is they are literally pushed together by the pressure of the entire matter universe pushing in. And that is simply how gravity works. Now, it doesn't act at a distance, though. It's still piece by piece, like giant chains reaching out. Because these balls of matter, the larger ones are visible. Like, for example, atoms have pieces that the waves bounce off of that we can see. But there's stuff that's much, much smaller than electrons. Of course, very, very small balls, small balls of matter. And even the larger matter balls arrangements that we know of are actually made of much smaller pieces. And they're just, they found this out in more recent years that, you can even break down the protons, down into things they call quarks and things. But it doesn't matter what you name them. They don't actually have properties to them. They're not. There's no electric attraction. There's no magnetic attraction. There's no gravitational fields. None of that stuff exists. It's all a result of the interaction of these things with the ocean of matter. And that's what I'm demonstrating with all this stuff, is that it's the ocean of matter that causes all these things to happen, and why. So gravity, like other fields, have to do with the matter arrangement. If you have larger balls, the pressure of the matter universe brings in the matter piece by piece to fill the cracks, the holes, all the way down. And so when you jump up off the earth, or if you're above the earth, you fall to the earth, and your matter with all its thickness and all the larger pieces come down and start filling the holes piece by piece all the way down until you hit the earth, and you can't fill any more holes because you've already filled all the holes you can because you're on the surface. And that's it. That's basically gravity. The reason why it seems like it attracts at a distance. The reason gravity seems like it's attracting at a distance. Let's say that this is the Earth right here. There, Earth. And out from the Earth, there's there's these little, they're big balls relative to the matter universe, but these balls, they go up, well into outer space, in arrangement, and these balls want larger balls to be around them. But these balls are microscopic. They're so small you cannot see them with a electron microscope, because the electrons are as big as what you can see with an electron microscope. You can't see these balls because they're smaller than electrons, but they're still big relative to all of the matter out there in the matter universe. All the matter that's up here and stuff in the matter universe, it's relatively big. But it gets finer and finer as it goes out into outer space. So anyway, it's like a chain that pulls in the matter, because whenever a large piece comes in contact with it, and there are larger pieces beyond it, what happens is it follows down this chain of matter that's around the Earth. So it goes in and it fills this hole, and it keeps going, and it goes in and fills this hole, and it fills in this hole, and so it's literally sucked to the Earth. Until it touches, until it's to the Earth. So
it's not a coincidence that gravity acts like a suction where it's much more powerful near the earth, just like you'd have a vacuum cleaner. You know how you have like a nozzle to a vacuum cleaner, right? And it's sucking a lot of stuff right near the surface of the hose of the vacuum. And that suction there is powerful, and it goes much weaker as it goes out and out from the hose of the vacuum. The same thing happens with gravity too, where it's filling these holes, because it's being sucked into these holes, and it'll keep flowing. It'll keep bringing the stuff in as long as there's stuff behind it to push it in. In fact, the very fact that it's sucking stuff to the earth demonstrates that there's an ocean of matter out there, proves it beyond a shadow of a doubt that there's an ocean of matter out there, because if it couldn't push from what's out there, if there wasn't pressure out there, it couldn't suck the larger pieces down to the earth. So even gravity demonstrates that there's an ocean of matter out there, and that we're all just like fishes in it. So we can see gravity is not a force. It's not a field. It's simply chains of matter, larger pieces, being more efficient arrangement around other larger objects. So the larger matter demands larger objects. To a point. And that's another important point as well, because it can get to a point where an object is so dense that the opposite of gravity occurs.
You see, when I was looking into it, and I didn't even know about the history of other people who had looked into it. I called it Riptio because it was like it was ripping apart stuff. It was like it was spreading it out. Einstein called it the cosmological constant, and then he reneged on that idea. But it doesn't matter what you call it. It's the idea that if there's gravity, a force that brings stuff together, then there must be a force that opposes it to pull everything apart. Because if everything just came together in the universe, the universe would eventually be just a ball. But if everything only came apart, then eventually, the whole universe would just be expanded. So the idea that there had to be two equal and opposite forces, gravity and, like Einstein said, the cosmological constant, or what I was saying, Riptio, doesn't matter what you call it, because none of those forces even exist. Gravity doesn't exist as a field, and Riptio, or cosmological constant, or whatever you want to call it, it doesn't exist either. It's just a function of the stuff that we're all in. It's a function of the ocean that we're all in. The stuff comes apart if it gets too dense for what's around it. And that's a very important point, because you see, everything is held together by pressure. For example, why are all protons round? Why are all electrons round? Why are all atoms, nuclei, basically round? Why are all atoms in general basically round? They're not perfectly round. They got bumps, of course, because they're composed of little pieces and stuff, just like what you'd expect. But why are all things, the pieces and all that basically round? Well, it's because they're being held together by pressure, by the pressure of the ocean that's around them. That explains why everything is round, why you can only use balls, and why you don't have an option to use flat surfaces to cover the matter. more efficiently. But the most efficient way you can cover the matter, in the universe, the big balls are rarer, and the smaller balls are much more common, and that's why everything wants the big balls, to a point. But if this big ball is really big, because it's composed of many pieces, if it doesn't have enough dense pieces around it, it will fly apart. Why? Because why will it be ripped apart by what I used to call riptio? Because the little balls that are holding it together can't hold it together enough, and its internal pressure, it blows it apart. And the smaller pieces rush in to fill the holes around the pieces that flew apart. So the pieces, why would the pieces fly apart? Because when the pieces separate, because there's not enough pressure to keep it together, a chunk of this piece will fly out, and this piece will immediately surround it because it's gravity. It's gravity. In other words, this guy wants its matter, it's covered, its surface covered, and so it'll rush in and fill around the pieces. But there's like a lot of these balls all over the place, all around it and stuff. And so and it grabs it and it brings it away. And that's why things fly apart. That's why, that's why evaporation. That's why radiation, and that's why fast radiation. In other words, that's why fission and fast fission, and again, it's just the opposite of gravity happening, where if it's not enough pressure around it, it will fly up. To keep it together, it'll fly apart. And this happens on every level, for very, very large objects in space to the very, very small, even with atomic nuclei. Have you ever wondered why every element above, larger than bismuth atoms is radioactive? That's why. It's just too big for what it can get around it to help hold it together. So that's why gravity, that's why riptio, and it's all caused by the ocean of matter that we're all in. In other words, gravity doesn't really exist. We can name the why the larger pieces come together, but once you see why, that it's all because of the pressure of the matter universe pushing in, then you understand why gravity happens, or you could say gravity happens because gravity doesn't exist, and why riptio happens, again, why riptio happens because riptio doesn't exist either. The things that are inevitable if you have pressure in an ocean of matter. Next video, I may talk more about radiation.